Let's see.
All right, hey everybody, I hope you guys have been doing well since the last time we spoke. Today we're gonna do a deep data dive on episode 3, the difference between data science and machine learning, and hopefully talk or illustrate the difference between these terms that Laura and I have been using for the last couple episodes, and to show that they're not exactly interchangeable.
Yes, definitely. So I guess first off, let's think about, like what's the difference between data science and machine learning? If you ask me, they're not really like a difference. They're sort of overlapping in that machine learning is sort of a subdiscipline that exists inside of data science. So it's entirely possible that you can have data science without machine learning, but I feel like it wouldn't be possible to have machine learning without data science.
So, I kind of agree with you somewhat, but I think going back into history, I think in the last 50 years ago, there's been artificial intelligence, and for the most part, it hasn't been getting a lot of traction, but with machine learning, I know that the notable papers have been written in the mid to late 90s, and I would argue that machine learning is an application of artificial intelligence to get it moving along. In terms of what we said about data science being used to get insights and make a decision, machine learning does meet that criteria, but as you mentioned, machine learning is also not needed to make a decision, because machine learning, from a business analytics standpoint, it's predictive analytics.
Mm-hmm. Yeah, where we're trying to, well, oh no, I think BJ's frozen. Okay, you were frozen for a second.
Like you froze there.
Oh no, we're all frozen. Damn it.
All right, where did you lose me?
Okay, you were talking about machine learning and being predictive.
All right, machine learning is a part of predictive analytics, and that uses an algorithm or a model. But taking a step back, or doing things on a more industrial engineering lens, there's something called heuristics, and that's making decisions. Could be rules-based, but it's still addressing the need of making a decision, but it's not using the frameworks of a machine learning model to do so. And with that, there's like optimization. There's something that's called prescriptive analytics, and I do need to brush up on a definition of it, but from what I understand, it's recommending a specific path going forward, as opposed to a machine learning model, which in some cases will say, with this feature set or independent variables, here are what we think the labels are, if it is a supervised problem.
Yeah. In which case, that brings us to our next topic is, we're talking upon maybe like different types of machine learning. And one of the things that you just mentioned was supervised machine learning. And I know we covered there's supervised, unsupervised, semi-supervised, and reinforcement.
All right. So with supervised, as I mentioned, there are labels that one has, and one makes a model with a holdout, or uses a holdout data set to validate the model's predictions against the label set one already has to assess the performance of that model.
Yeah. So I guess like trying to think of like a practical example is, like all the different things for predicting churn. If you imagine looking at like any of the Kaggle challenges. So that's an example of supervised learning because the data that they'll give you will involve a bunch of different features about each user, but it'll very specifically have that sort of label or outcome where it says like we know did the user churn or not, like in each row for like each user we know did they churn, yes or no. So that's an example of labeled data set where we know what happened to that user or that session, and we're trying to see if we can use the other data there to, I guess, predict whether or not a user will like churn, in which case like have that outcome.
Yes, the churn example is like a very good and classic example. Another one is having a set of emails and categorizing or classifying the ones that are spam versus not spam.
Yeah, and in this one, usually in this case, like your training data set will have your emails and then a label that somebody has very generously put probably manual time into labeling them as spam or as not spam, and then that gets used as our training data set for the model to predict whether or not an email will be a piece of spam. But at the end of the day, we know what is and what isn't spam because, well, I guess it's labeled. Like somebody went and actually took the time to apply the label. Well, once again, it's kind of a case of like we know what happened. We just need to like be able to predict what will happen based on these different features.
Right. And what we talked about so far is classification, and I think it's important to note that for regression problems, uh, those could also be considered supervised as well.
Yeah. And I guess the main difference between like a classification and a regression is that a classification problem is one where you can be classified into a bunch of different categories, but generally speaking, your outcome or your label is going to be categorical. Like did a customer churn or not? Are you going to classify a customer as like a non-user, a light user, medium, or like heavy user of your service? These things are all like fairly discrete, but maybe if you want to think about regression, in which case your outcome is going to be a little bit more continuous. So, I mean, I guess going back to like my public health training, one of the classic examples of regression is once again using like a linear regression, which is using your set of like labels to try to predict something that you really can take on a large number of values, such as somebody's like body mass index. So, let's just say realistically, a person's body mass index can be anywhere between like 17 and like 40. So, as long as you're between those two, you can be really any of those. And that's an example of a continuous outcome. And then maybe some other examples of something that's roughly continuous might be the number of minutes that you spend browsing a company's website, or maybe, the current balance in your bank account. So those are things that a company could be using machine learning to predict, such as, if they know however much information about you, they might want to try to predict how long you'll spend per session on their website. Or if you're a bank and you want to predict what a user's balance is going to be, and those would probably be regression problems.
Yeah, I think that's a very comprehensive definition, and I like it quite a bit. And although we can talk more about supervised models and how to evaluate them, I think we should shift gears just to give a contrast or a juxtaposition to the other methods. For example, with unsupervised, that's a case in which there are no labels. And the million-dollar question is, what does one do then?
Yeah. So that's always a tricky one because what you can do in this case of unsupervised. So I guess here, going back to our classic examples that we've talked about for, like a Kaggle competition for churn, it's just saying that we have all of the different features that we know about each user, but now it means we don't have that outcome. We don't know if somebody churned or if they didn't.
Right.
Then going back to the idea of if you're going to, approve somebody for like in advance, you don't know whether or not that person was approved for the advance because at this point that data just does not exist for whatever reason. Or, if you want to predict a person's body mass index, you have all these different features about a person, but you don't have their body mass index. Or if you're trying to predict how long a customer might spend on a company's website, all these other things about a customer, but you don't know how long they spent. So, you know, in terms of, I guess, both like classification and regression type, I guess you would say that do they have analogs for unsupervised? I don't really know, but I'm just thinking about it that way, where like unsupervised is simply you don't have that label, and what you're really maybe looking to do is see if there are patterns among your data, because
Well,
you can't predict the outcome, but there are
well,
other things you can
I
do.
think it goes back to the definition of getting insights from data. And the most, well, probably one of the most basic examples is clustering. So if I want to make three different groups, I use a distance metric for the different feature sets.
Yeah.
And then um, here are the attributes of these three different groups, and does it make sense from a high level? What does it tell us? And is three the appropriate number to use? And I think just having that gives us enough incentive to um, go a little bit further. And another example would be, well, it's something I definitely need to brush up on, but at a high level, it's latent dirichlet allocation,
Mm-hmm.
or LDA, and that's being used for topic modeling. So one has a collection of news articles, for example, and if I want to get the top 10 categories and the major words that are being mentioned or use to discriminate between the 10 categories, I can do that. And I would say that that's an unsupervised way because these categories are not defined beforehand. And it's up to the data scientists, it's up to maybe people on the business end to see if those categories can make sense. And there's also the possibility that something that's initially unsupervised can become supervised either as we get more information or we see something that's different about the different groups and we start to make labels. But I think that it kind of overlaps with semi-supervised learning.
Yeah, I think so too. I think something that was also once mentioned to me when I was interviewing was the topic of, how do you try to validate like an unsupervised machine learning problem? And the person said sometimes, the best thing you can really do is see if you can grab a small subset of that data and just try to turn it into a supervised problem. Maybe get like 5% of your data and just try to hand label the outcome if you have some ability to do so. because sometimes it's maybe just a little bit easier to know maybe like how accurate or how precise your machine learning model can be when you know what the actual outcome, like what actually happened is. Because in a supervised problem, when you're looking at metrics of accuracy and comparison, you're looking at maybe like what is the actual outcome that actually happened and what did your algorithm predict. And then there are ways of deriving, looking at like actual proofs of predicted, sort of like how far off the mark were you.
So in other words, I'm just trying to digest what you just said. So you said there's like an accuracy, and then you're saying like how far off
I
from
guess,
the
yeah, I guess how far off the mark is very like thinking about it in a conversational sense. I guess, the actual metrics more or less being like accuracy and precision when you're trying to determine how well did your supervised learning algorithm work.
Well, I understand those metrics for supervised learning, but I'm trying to think about how that's being applied to the semi-supervised, because you have only a small set of labels, and then you have something that's unlabeled, and um, I
I guess I
assume that.
feel like in that case, you could probably only get those metrics on that small set that's labeled. Like I wouldn't even apply it to the unlabeled bits.
Hmm. Well, I mean, it's something that we both need to research and discuss further, or bring on a guest to talk about it. But um, my inference at this particular moment in time, and we'll correct ourselves if we're wrong, is that having that small label set will give us part of the answer of seeing if the clusters or whatever else we have, if it makes sense, or it kind of guides us towards. Um, hmm. Well, I mean, I would need to think about if the goal is to make everything labeled, or to still move forward with that small labeled set, because as you did mention earlier, it does take time and manpower to label everything. And I'm just thinking aloud now, if uh, decisions and insights can be made even if we only have like a small set that's labeled. But that's something that uh, we can look into later on and talk about in the future.
Yeah.
Um, in the meantime, do you want to talk a little bit about reinforcement learning?
Dude, I don't really know anything about reinforcement learning aside from
Well,
that it exists.
I think on a low level, all of us don't understand Bellman curves or whatever, but I think on a high level, we all know about self-driving cars, and um, a car obviously makes mistakes, and the way that those mistakes are fixed is that there is a penalty system um, to prevent those mistakes from reemerging in the future. And um, if I understand it correctly, with machine learning, well, at a high level, there's data, one trains it, one fits the model, um, then that's it. But with reinforcement learning, the AI agent continually and constantly learns upon a different set of penalties that are being imposed. And um, although deep learning's pretty hot now, from what I read a couple of years ago, the what's going to probably come afterwards is um, a growth in reinforcement learning.
Yeah. Yeah, that's the application that I've definitely heard of as being the most associated with reinforcement learning is self-driving cars.
All right. I know we can talk a lot more about machine learning, but I think with what we just spoke about, I think that should hopefully give people like a very high level overview of the differences between the methods that are out there.
Yeah. Do we have anything else we need to cover for this episode?
Um, well, I'm sure we probably do, but oh, I'm just like looking at the outline. Maybe this part would be edited out, or maybe not. We'll see. Um, I think I'm pretty satisfied.
Okay. All right. So that wraps up episode 3 of Deep Data Dive, data science and machine learning. We hope you've enjoyed this episode and hope to see you in time for the next one. Thank you.
All right. Yay, we can both
Yay.
have dinner.
Yay. That's 3 episodes. That's just pretty good output for like the first day of recording.
Yeah, got a trilogy there.
Yay.
Have like a Star Wars opening crawl.
Yay. Of course. Guess all I have to do is just do this. Sweet. I think we can turn off recording now.
um, yeah, I suppose we could.